Problem number 12 is asking you to find a power series centered at 0 for the function natural log of 5 plus x. So if I want to go ahead and find a power series definition for that, what I'm going to do is I'm just going to use the original definition of the power series that we learned, 1 over 1 minus x. But first off, I need to be able to get my function into that kind of form. So if I'm starting with natural log of 5 plus x, I need to get this into a 1 over 1 minus x form. So to do that, what I'm going to do is I'm going to look at its derivative. So if I take the derivative of this term, I end up with 1 over 5 plus x. This is a series, or this is a function that I can use to find a series. So let's go ahead and let's try to find a series from this. So if I need to use the definition 1 over 1 minus x, I need to get rid of this 5. So what I'm going to do is I'm going to pull out a 1/5 from the equation, and I end up with 1 over 1, turn this plus into a minus minus, so this is negative x over 5, and there's another negative inside there as well. So now I have 1/5, 1 over 1 minus negative x over 5. So I can find a power series of this function and just multiply it by 1/5. So I'm going to go ahead and do that. I'm going to say that my series is 1 over 5, n equals 0 to infinity of negative x over 5 to the n. So if I go ahead and I simplify this a little bit, I end up getting summation n equals 0 to infinity of negative 1 to the n x to the n over 5 to the n plus 1. This 5 to the n plus 1 comes from the 5 to the n that I ended up with this term by splitting it up and multiplying that extra 1/5 outside. So that 1/5 is 1 over 5 to a first power. So that's where that first power comes from. By multiplying powers of the same base, I can add those powers together. So now I know that this is the definition for 1 over 5 plus x. So all I have to do is integrate both sides to find the actual definition for natural log of 5 plus x. So by integrating both sides, I end up getting natural log of 5 plus x is equal to summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1, divided by n plus 1, 5 to the n plus 1. And of course, because I'm integrating indefinitely, I need to add a plus c to the end of this series. And now I need to solve for that plus c to see what that value is actually going to be. So the way I'm going to do that is I'm going to plug in my center value that was given to me, so it was a equals 0. So by plugging in that value into here, I can cancel out my series and find out what the constant c is equal to. Remember, I don't want c to be a function of my series, so I need to plug in a value that causes it to go away. And in this case, x equals 0 will satisfy that. So on this side, I end up getting natural log of 5 is equal to 0 plus c. 0 comes from plugging into the series. So c is equal to natural log of 5 in this case. So what I can do is I can actually just go ahead. Right, this is natural log of 5. So now this is my series definition, but the answers are a little bit different. So the answers not only want the interval of convergence, but they also want n equals 1. So what we need to do is we actually need to re-index this power series to be able to get it into a form that will match our answers. So what I'm going to do is I'm going to say that natural log of 5 plus x is equal to, now I'm going to move this index forward to n equals 1. By moving this number forward, I move everything back 1. So that means that this becomes negative 1 to the n minus 1. This becomes x to the n. This becomes n. And this becomes 5 to the n. And of course, this plus natural log of 5 is still out on the side. And that's not a function of n, so we don't change that at all. Now, this matches one of the forms that we need. However, it doesn't have a negative 1 to the n plus 1. It has negative 1 to the n, it has negative 1 to the n plus 1, but we have a negative 1 to the n minus 1. Negative 1 to the n minus 1 and negative 1 to the n plus 1 are actually the same value. So regardless of the way we write it, negative 1 to the n plus 1 and negative 1 to the n minus 1 satisfy the same condition. So we can write it as either a plus or minus, and the answer is still correct. So in this case, looking at this value, we still need to find the interval of convergence. However, we know that there is a shortcut. By looking back at our definitions of Maclaurin series, we know that this actually looks really similar to a Maclaurin series that we've learned before, and it's actually at the top of the page. It says natural log of 1 plus x is equal to summation n equals 1 to infinity, negative 1 to the n, x to the n over n, and that's also an n plus 1. And that has an interval of convergence of negative 1 to 1 with a parentheses around the left, so exclusive to the negative 1 and inclusive to the 1. So this matches the same form that we had before, except this is a 1 and we had a 5 before. What that means is that we can actually base the interval of convergence off of that. So if this is negative 1 to 1, all this series should be is this should just be negative 5 to 5. And that would also have brackets and parentheses around it. And a way that you can test that is you can plug in these x values into your series and actually see if it matches that it should be exclusive on this side, which means it would be divergent when you plug in negative 5, and it would be convergent when you plug in 5. So looking at all of that, that gives us a final answer of C. And this was our final power series with the interval of convergence in it.
The Teaching Center, UF's Learning Resource Center.